All right, so welcome everybody to today's class in Mathematics 1. Unfortunately, that projector over here is not working today, but I guess we'll have to do with this one. Just switch up the lights here so you can see that better. Tasks for today. First, let me remind you that today is the last day you can submit the evaluation, and I would be very grateful if you did so. Then, at the end of this lesson, we'll also take a couple of minutes to elect your semester speakers. So that if there's something that you would rather not tell me, but you still have a complaint, you can always tell them, and they will then forward that to me. And then the plan for today is to go over some more problems. I hope I'll be able to address the requests, or most of the requests, from the tweetback questions. If there's any questions left, we'll hopefully also address those, if I can. And otherwise, we'll just take some time to practice today. So, as usual, I brought a few problems from former exams, sorry. I haven't written down the specific exams, but most of those were on actual exams. Here's one of a type that you probably haven't seen up to now. So we have two lines in R2, the plane. The definition is here in the problem statement, and the question is to determine values for these three parameters here, alpha 1, alpha 2, and beta, such that the line given in this way is perpendicular to this line here and passes through some specified point. So let's start with that right away. Take a couple minutes, see if you can solve that. Plus, that's alpha 1 x1 plus alpha 2 x2 equals beta. Let me clarify that. As usual, quick show of hands. Who of you is done already? Who needs more time? Well, maybe let's take 2 more minutes. All right, so let's see whether we can solve this one together. So this is a setting in the plane. That means we can start with a quick sketch in case we're not sure how to solve that. The first line is given as 1, 2 plus lambda times minus 2, 3. So this is a point the line passes through, and this here is the direction of the line. All right, so we have that point. Let's see, point 1, 2. That is about here. And then we have minus 2, 3. So minus 2 and 3, 1, 2, 3. So that is the direction, and that means the line will look something like, oh, sorry, I mixed up the directions here. My bad. Because I should be consistent here. So minus 2 this way. And then 3, 1, 2, 3. So that should look something like this. All right. So this is our x1 direction, this is our x2 direction. That's the line G. And then we have that line H. And H is defined in a totally different way. It's a solution of a system of one linear equation. And your task is to determine the coefficients on the right-hand side. Now, if you look at that, you could also write that as the scalar product of the vectors alpha and x, right? Alpha 1, alpha 2. Scalar product with x1, x2 equals beta. So geometrically, that means the scalar product between those two lines is determined by this equation. We want the line H to be perpendicular to G. That means the scalar product between the directions of G and H has to be 0. Right? So this here means scalar product between directions of G and H is 0. So let's take a look at that here again. Imagine the line G would pass through the origin. And if we're talking about directions, it doesn't really matter whether we translate that setting first, right? So this is G translated such that it passes through the origin. Then the direction of H would have to be something like this. Let's see. Something like this. Yeah, so this is H translated. Again, such that it passes through the origin. We'll take care of that 0.11 later. Important point is those two are now perpendicular. This G translated, that's very easy to describe. G translated is simply the same thing as G, but just without that 0.12. Right? Just do away with that. And what we have is lambda times minus 2,3 lambda in R. That's not G, of course, that's G translated. All right, so this here is the direction minus 2,3. Now what about H? If you want to describe the direction of H, minus 2,3. This vector here or something, oops, I want to do that in blue, of course. So we need this vector here or something that is maybe not the same length, but the same direction. That's the vector we want. Well, how do we get H to be like this? Well, the condition that we have is all points in H are perpendicular to all points on G, so all points on that direction. And that means points on H are perpendicular to this minus 2,3 direction vector. And that means the scalar product of that direction and the point on H is 0 for all x1, x2 on H. Right, so in other words, the condition is minus 2x1 plus 3x2 is 0. That describes this translated blue line. And of course, the line we actually want is the same up to translation, right? So all we need to do is we need to translate that such that it passes through the right point. In particular, that means it has the same direction, right? So these coefficients will be the same. How do you translate a line that is given by your system of linear equations? Well, you change the right-hand side. These coefficients take care of the direction. This takes care of the translation. So all we need to do is we need to translate that. Now translate that, meaning change the right-hand side such that it passes through this 0.11. Well, how do we do that? Well, we just substitute 1 into that equation. Into minus 2x1 plus 3x2 equals a general right-hand side beta, and then we just solve for beta. So that's minus 2 times 1 plus 3 times 1, and that is, of course, 1. Right, and that means our line h is given by all x in R2, such that minus 2x1 plus 3x2 equals 1. And so we have our alpha 2. Alpha 1 is minus 2. Alpha 2 is 3. And beta is 1. And of course, if you prefer, for whatever reason, you can multiply that with any factor you like other than 0. So any multiple of those values would also be correct. All right, any questions about this one? Yes. Could you repeat that? I didn't get part of the question. So you mean which vector? That minus 2, 3 vector? Yeah? Or is that perpendicular to G? So this minus 2, 3 vector, that is the direction vector of G. If you look at that sketch once again. So this is that minus 2, 3, right? That is the direction of G. And what we want is H, this blue line here, or that's a translated version of H, but that consists of all points that are perpendicular to that vector. So what we really want is we want the orthogonal space to the space spanned by that direction. Right? So that means a point on H is defined by the property, the scalar product of minus 2, 3, and that point is 0. And I'm talking about the translated version of H, right? The one that passes through the origin. Okay? So that's just the definition of perpendicular. Hmm? So what is alpha 1, alpha 2? Well, if you just write the scalar product here, what that actually is minus 2 times x1 plus 3 times x2, right? So that has to be 0. That means if you want a line that passes through 0, obviously these are the right factors. That's our alpha 1, that's our alpha 2. And now all we need to take care of is the translation, so we need to modify the right-hand side accordingly. And that will yield the beta. Does that answer the question? Good, thanks. Any other questions? Maybe let's scroll down again. Yes. Sorry, which vector? The vector 1, 2, 3? No. Minus 2, 3? So you're saying minus 2, 3 is not perpendicular to what? To the same vector. Yeah, sure, it's not. No, I know. The problem, okay, I think I understand where you're coming from. So the point is, this vector here is the direction vector of G, right? It's not the direction vector of H, and I'm not using it as a direction vector here. H is given in a completely different form. H is given as the solution set of a system of linear equations, right? That means alpha 1, alpha 2 are not the direction of H. Yeah, those are coefficients for a system of linear equations. Geometrically speaking, what we have here is the normal vector of H, right? The normal vector is one that is perpendicular to H. And that's just the direction vector of G because we want them to be that way. Okay, so if H is given in that way, these coefficients do not represent the direction, but they represent a normal an orthogonal vector to that direction, geometrically. 3, 2 is perpendicular to minus 2, 3, yeah? So, yep. No. No, so if I said something like I want 3x1 plus 2x2 to be 0, that would mean I'm looking for all points that have a scalar product like this, right? 3, 2, scalar product with x is 0. That means in that case, I would be looking for points that are perpendicular to that vector, not that direction, right? So 3, 2 is a point that would fulfill this equation here. Minus 2 times 3 plus 3 times 2, that obviously is 0, right? That means 3, 2 is in this H translated, right? That's one of the points that is on that translated version of H that passes through the origin. It's not the direction of H. So if we wanted H to pass through the origin, or if we just didn't care, then of course this equation here, that would already be the solution, right? So any line that has this coefficients on the left is perpendicular to G. And if we change the right-hand side, all we do is we translate this line, right? Two lines that look like this or like that, they are all perpendicular to G. Because these coefficients here, that determine the slope of our line, right? That beta, the lower right-hand side, that simply depends how we translate it. Okay, and that's why this works here. So of course, if you know all this, you could have said right away, well, this here needs to be a normal vector to my line H. So these are the coefficients alpha 1, alpha 2 I'm looking for, and that's just determined beta. And now you know this, hopefully. All right, any other questions? Otherwise, let's proceed to the second problem that I have prepared. Someone has asked for a projection of a vector onto a plane. So we do just that. Here's a plane. Our vector space U is a plane in 3D space. And the task is to determine the orthogonal projection of this vector V and this vector W onto the set U. So again, I'll give you a couple minutes to do that, and then we'll talk about possible ways to attack that problem. What's the orthogonal projection? So basically, I have this plane here, right? And I have a vector. Let's say they all pass through the origin, which they do, of course. And then the orthogonal projection is I'm taking this orthogonal here, orthogonal to the plane, right? Points to the apex of this vector here. And the orthogonal projection is the vector in the plane that corresponds to this, right? So what I do is I decompose my vector into one vector that is in the plane and one vector that is orthogonal to it. And the projection is the part in the plane. Okay, we did this in 2 dimensions multiple times. You might remember, let me just quickly sketch that. You might remember we did things like this. So let's say here is our space U. A little larger, this is our space U here. And let's say this is the vector we want to project. And what the projection then does is basically it takes a decomposition of that vector into one part that is orthogonal to U, one part that is inside of U. And let's call that one V here. And this red part, this is the orthogonal projection of V onto U. Right? And of course we can do the same thing if U is not one-dimensional, but as in this case, two-dimensional. Quick question, who's done with the orthogonal projection of V already? Just V? One, okay. Okay, quick show of hands, who's done already? No one. Okay, I guess we need a few more minutes for that. All right, so maybe let's take a look at that problem together. Just out of curiosity, who thinks they solved it? Who has given up? Okay. Just for your information, the exam question actually consisted of just the first part. So this W part was not in the exam question. And of course, that makes the problem a whole lot easier. So in the exam, I would expect you to solve it in like 3 minutes or so. Let me show you why. So this vector v, 1, 0, 1. Did anyone come up with a projection of v onto u? What's the result? Yeah, it's the same vector. Why is that? Exactly. So the vector is a linear combination of those two, right? You can see that if you just add those two vectors, the result is V. So what does that mean? That means it's contained in U. U is the span of those two vectors, so V is contained in U. Well, if you project a vector onto a space and the vector is in that space already, what happens? You get the same vector. You decompose it into a part that is in the space and a part orthogonal to it. Well, there is no part orthogonal to it, so the decomposition is just that vector. And that was the intended solution. Right? So that's the first way to solve at least that V part. Yeah, so that V is equal to just the sum of those two vectors, and that means V is contained in U. And for that reason, the projection of V onto U is again V. So that was a solution I would have expected in the exam. Yeah. So when V is not A, like W, for example. That's why I included that. Right, so let's go about the other methods that would also work for W. Second approach. So basically, we know two formulas that we can apply for this projection thing. One is, that's probably the most universal, you compute an orthonormal base of the space that you want to project onto, and then you just project your vector onto all those vectors of the orthonormal bases, and you add up the result. Right? So first thing is we need an O and B of U. U is given by these two vectors. Quick look at those two vectors to verify that they are not yet orthogonal, so we actually have to do some work, and they are not normalized. Okay, so we do Gram-Schmidt. First basis vector is the normalization of the first vector in U. Let's just start with this 1, 1, 0. The length of that is square root of 2, so we just need to normalize that. Right, that's the first part. Then for the second part, one of these Gram-Schmidt steps that looks like this. We take the vector, the second one, so 0, minus 1, 1, and we subtract its projection to the space spanned by B1, so that we get the orthogonal part back. Right, so what we want is we want to take the scalar product of this vector with our B1 times B1. And we subtract that from the original vector. Okay, so what we have here is, we take out that factor here, 1 over square root of 2, and combine those two so we get 1 over 2. Then the scalar product of those two vectors here, that is 0 times 1, minus 1 times 1, that's minus 1, and another 0, so it's a minus 1, times this 1, 1, 0 vector. All right, so we get minus 1/2 times minus 1, that's plus 1/2 times that vector, so the result is 0 plus 1/2, that's 1/2. Minus 1 plus 1/2, that's minus 1/2. And 1 minus 0, that's just a 1. Okay, let's take out the 1/2 factor, then we have 1 minus 1 and 2. And just a quick check to see if those are orthogonal right now. Right, so the scalar product of B1 and this direction, that would be 1 minus 1 plus 0, so that's 0. Works. Okay? Of course, you don't need to write that down in the exam, but you should always quickly verify that this is correct before you continue with the next steps. And of course, for checking whether two vectors are perpendicular, the length doesn't matter, so I can just forget about this factor here when I do the check. And now let's normalize. So B2, And for the normalization, again, I just use this vector here. I'll normalize it to length 1 anyway, so whatever scalar factor I have here, I can just forget about that and normalize any multiple I like. And the length of this one is, let's see, 1 plus 1 plus 4, that's 6, so the length is the square root of 6. And now, of course, I normalized this vector here, so I put this vector here, and please don't include the 1/2 if you do it this way. Or, of course, you can normalize including the 1/2, it's also fine, but it will look a little more complicated. But should get you the same result, of course, right? So here we have our ONB. That means we can write U as the span of 1 over the square root of 2, was 110, and 1 over the square root of 6, 1 minus 1, 2. Okay, and now subsequently we can use that OMB to compute projections. So now let's project W and V onto U. Let's do W one more time just to verify that my argument before was correct. So what we need to do here to compute the projection of V onto W is we need to project that vector onto each of those and simply add the result. Right, so first we do the projection of V, and V was 1, 0, 1 onto this first basis vector. Okay, so this here is the projection of V onto the space spanned by B1. And then we add the second. We just use the second basis vector here. And this is the projection of V onto the space spanned by B2. And those two are orthogonal, so there is no common part in that projection. That's why we needed an O and B in the first place, right? So that means we can add up those two parts without any double counting. All right, what do we get? So the first part is 1/2 times, let's see, the scalar product is 1 plus 0 plus 0. That's easy. Times 110. And that second part is 1 over 6 times, and now the scalar product is 1 plus 0 plus 2, so that's 3. 1 minus 1, 2. And hopefully, let's see, the result is correct. That's 1/2 plus 1/2, that's a 1. Then we have 1/2 minus 1/2, that is 0. And then we have 0 plus 2 times 1/2, that's a 1 again, so all looks good. Right? So that's how you do this projection onto a space spanned by more than one vector. Just do the same thing, combine the results. Yeah. Why do we need an orthonormal base? So that the projection is correct. If you just use an orthogonal base, of course you still don't have any double counting, that's okay. But the projection on each of those individual spaces wouldn't be correct anymore. Because in the projection, you would include that scalar factor for the vector, right? So you have a vector that has not length 1, so that length will, of course, influence the scalar product and the vector itself. So the projection will be too long or too short. Yeah, that's the problem here. You need a normalized version for that to be correct. Yeah. So in this specific example, we are in three-dimensional space, right? That means the space can be decomposed into that plane and the orthogonal space. Yeah, those completely decompose the space. That means you could also have tried to find a vector that is orthogonal to the plane, guessing, cross product, whatever you like, and then try to find the right decomposition by, for example, solving a system of linear equations. That would have worked in this case as well. Gets harder if if the dimension gets higher. Sorry? So that length will influence the scalar product. If you use a system of linear equations to solve it, you don't have a scalar product involved there. And the solution will adapt to the length in the correct way. Right? So that will work no matter how long the vector is. But as I said, that works for 3D space, for 2D space. I wouldn't use that for higher dimensions. It gets tedious very quickly. All right, so just to be complete, let's also do the projection of W onto that space, and then I'll show you the third method that you could have used. Again, same thing, yeah, I do the projection onto all of those two basis vectors individually. Let me just copy over the basis. Right, so that projection is W is 1 to 1. So we have 1/2 times 1 to 1, 1, 1, 0 times 1, 1, 0. And you'll notice I took out those 1 over square root of 2 already and combined them. And then I have 1 over 6, 1, 2, 1, 1 minus 1, 2. Yep. 1 minus 1, 2. And what do we get here? Let's see, that's 1 plus 2, that's 3 over 2. 1, 1, 0. Plus, and here we have 1 minus 2 is minus 1, plus 2 is 1 again. So that's 1 over 6, 1 minus 1, 2. And that means, what do we have here? Let's see, 3 over 2, that is 9 over 6 plus 1 over 6, that will be 10 over 6. Again, 9 over 6 minus 1 over 6, that will be 8 over 6. And then we have 2 over 6. If we take out that factor, 1 over 6, that is 10, 8, 2. So that would be the projection of W. All right, any questions about this method? Then let's look at one last method that you can also use. So third approach. Remember we talked about the least squares method, and in the context of least squares, we were faced with systems linear equations that were infeasible of that form. A times x equals b, infeasible equation. What we did is we projected, so our solution was to project b onto the column space of A. And we did this in the following way. We solved the system of linear equations A transposed AX equals A transpose B. We got a solution that we called X hat. And then this projected version called B hat was simply given by AX hat. Right? And that was the projection of B. Of course, we can also use this method in this setting here. In this case, we would have to write U as the column space of a matrix. Well, that's easy to do because U is given as the span of two vectors. So let's just use that vectors as columns of a matrix, right? So that is the column space of the matrix given by 1, 1, 0, and 0, minus 1, 1. And then we have our B. That's the thing that we want to project onto that column space. So B in our setting is either V or W. Right, let's just do that for V once again because the computations are probably easier. First thing we need is A transpose A. And of course that can be used for both of those computations. Oops, sorry, there's a 1 here. So let's see, that is 2, minus 1, minus 1, and 2. And remember, if you do that, the result should always be symmetric, so it's worth a quick check. And of course, this is symmetric here. And then we need A transpose B. So in this case, A transpose V. So this is A transposed, and our vector V, that was 1, 0, 1. So we get 1 and 1. And of course, this is a step you need to do for each of those vectors, right? If you also want to do it for W, you have to do that one again. Then we just solve A transposed AX equals A transposed V. Right? So we have this matrix here and this right-hand side. And to solve this, let's say we swap the columns first. Oh, the rows, sorry. So I have a minus 1 in my pivot position here. And then I want to add 2 times the first row to the second one. And I will get, let's see, what do I get? 0. That's plus 4, that's a 3. And plus 2, that's again a 3. And then I can solve. My x2 is 1. And my x1 is 2x2 minus 1. So that will be 2 minus 1, and that's again 1. Okay, so now I have my x hat vector. The solution to this system, that's simply 1, 1. And then I can compute this projection. So the projection of V onto U is then given by A times x hat. So A is 1, 1, 0, 0 minus 1, 1, and x hat is 1, 1. And the result is, unsurprisingly, again, 1, 0, 1. Right? So that is also a method that works for problems like this one. And of course, you can do the same thing with W. I'm going to spare you the trouble, I guess. Questions about this? That does not seem to be the case. Good, so we have some more time. Let's take a look at, oh, this is something completely different for a change. Linear subspaces, that should be quick. So I'll let you take 2 or 3 minutes. Yep. All right, so as I said, that should be quick. Maybe not to write it all down, but to get the idea of what to do here. So maybe let's quickly discuss that problem. First question, just a quick show of hands. Who thinks U1 is a linear subspace? Who thinks U1 is not a linear subspace? That is a clear majority, I'd say. And of course, you're right, because that statement here is just complete nonsense, as you have hopefully seen. So this here is a scalar product of this vector and this vector. The result is, of course, a scalar, right? So this here is in R, and this is not. No way to compare these two things. Okay, so that was kind of a trap. Bonus question, if I replace that by, let's say, 7, how about then? Is that now a linear subspace? Who thinks it is? Who thinks it's not? Again, a majority. Is it an affine subspace? Who thinks it is an affine subspace? Who thinks it's not? So I'd say we have a majority for not linear but affine, and of course you're right. Yeah, so now the point is, or the easiest argument is, this is a linear equation. The right-hand side is not 0. It does have a solution, it's not empty. It's not a linear subspace because it doesn't contain 0, because the right-hand side is not 0. But it's a translated version, so it's an affine subspace. And you can just say, well, we learned the system, the solution space of an inhomogeneous system of linear equations is always an affine subspace, and this is such a system. That's it. All right? Similar for the second problem here. So here we have a space that is defined as the solution set of 2 linear equations. This time the right-hand side is 0, and the solution set of a homogeneous system of linear equations is always a linear subspace. So that is the right answer here. And finally, what about U3? Let's again have a quick check. Who thinks U3 is a linear subspace? Who thinks it's an affine subspace? And who thinks it's neither? Yep, again, the majority is right. It's not one of those things, obviously. One simple argument is try to find a counterexample. For example, you could say that the point 1, 1 is contained in U3, that fulfills those 2 inequalities, but the point -1 is not. And of course, for a linear subspace, the negative point would have to be in the space as well. And to settle the question of affine subspaces, the origin is contained in U3. So if it's an affine subspace, it must also be a linear subspace. And it's not, so it can't be an affine subspace either. All right? So I guess we can take a look at one more quick questions about that before I go on. Otherwise, we can take a look at one more problem. Okay, so the question is the fact that this is an inequality, is that a problem? Let's say it should give you a hint into the right direction. It's probably not a linear subspace. But of course, I could just write, I could just like codify an equation into a bunch of inequalities, right? Like write those in a fancy way, and then it would still be a subspace. So it's not, you can exclude that. But my first idea was to try and disprove that. All right, then maybe let's take a quick look at this problem. I've been asked about that already, so some of you have found that problem already. Maybe let's take 5 minutes to see if you can solve that. Quickly try and give you an idea of how to do that. All right, again, quick show of hands. Who thinks they solved the problem? Wonderful. So let's take a quick look. I've already written the first step down. So in the hint, it says add everything to the last row, and that's what I'm doing here. By the way, this is how the matrix looks, right? So I have 4s in the diagonal, 1s everywhere else. So if I add everything to the last row, well, what happens is this here all stays the same. And in each column we have 1 4 and n minus 1 1s. So this all sums up. And that means we have the entries 4 plus n minus 1 in all entries here in that last row. Now what's the next step after that? Yes. Yeah? Go ahead. You. Pull it apart again. I think the goal is right, but pulling it apart might, I think that's hard. Or not immediately clear? Other suggestions maybe? Yeah? So you're taking out the factor in the last row, and then you have all 1s, and you subtract that. Yeah, you could do that. Or I could just work with columns. Similar result. Let's try that, because it's quicker. So the entries in that last row are all the same, and I want to produce zeros, right? My goal is to produce as many zeros as I can, and one way to do this is take, for example, the last column and subtract that everywhere. Right? What happens if I do this? All the entries in that last row become 0, apart from that last column. Of course, that stays. And what else do I have? Well, what I get here, and this is of course wrong, right? There's 1 here, because the 4 was in the last row, my bad. What else I get is the 4s, so I have only 1s here. I subtract that from every entry, so the 4s here become 3s, and the 1s become 0s. Right, so my result looks like this. I have 3s on the diagonal up to that point, 0s everywhere else, and of course 0s up here too, and I have the 1s here. So now I have a matrix that is triangular, and for a triangular matrix the determinant is simply the product of the entries on the diagonal. So those are all 3s, with the exception of the last one. Means I have n minus 1 3s, and then I have this 4 plus n minus 1. And that should be the result. Questions about this? Otherwise, please come up for the election of the semester speaker. So I'll hand it over to you guys, and I'll see you in a couple of minutes for the exercise classes, hopefully, or on Monday.